Yeah, thank you, and welcome to the presentation of the event processing engine Tornado. I'm also happy to welcome here next to me the core developer of the Tornado engine itself, Francesco Cina, and he will get
Pleasure to meet you.
In action then in a few moments. Just a few words about me. So I am Patrick Zambelli. I'm working for monitoring projects. So I am at the consultant side, implementing monitoring projects for WordPhoenix. It's about a decade that I'm active in this world for monitoring. First, starting by implementing modules, developing code based on Nagios solution, and starting then later in the consulting area on Nagios, and now on Icinga2. We are also partners of Icinga, and my classical installations of customer side is of various size, reaching up to 10,000 hosts, and as you might know, a couple of more services. So I have a variegated list of active monitoring, passive monitoring, and always a long list of to-dos which is coming in. Hey, monitor this new device. I have other services, events, whatever is coming from applications. Just a few words about WordPhoenix. We are a consulting company of the Word Group. We are located in the Alps in South Tyrol, Italy. And as I said, we are a partner of Icinga. We are doing IT operation projects. And next to our unit, there are other units doing also business software. We are doing ERP and CRM projects, and are partner of also other softwares we are installing in this time. So for today, the agenda, I would like to give you a view of the challenges I'm facing during the implementation of monitoring projects, and especially argue why we need the polling approach and event-driven approach for the implementation of the projects, and finally also leading to our decision to implement Tornado as this engine. In the second part, my colleague Francesco will introduce you about the design decisions, the architecture of Tornado, and we will conclude with a short presentation and a demo of this. So just to start, in my experience at the times of Icinga, also Nagios before, a traditional project starts with the polling approach. So I can simply go to a customer, deploy the various checks, and get really started with such a monitoring in an easy way. So we can say polling is an approach where I schedule at a static time interval. So I have time periods, I have check frequencies, the monitoring, and I get a specific state. So this means I have a well-defined result. I know which is the system I'm going to monitor, I'm connecting to, and I can therefore create already configurations with a good for the result I'm receiving back. And I can derive if this is good, bad, alert, and create also graphs if I have performance and trend to visualize. Another statement is it's a centralized configuration. This means I am starting with my monitoring system at the center, and I'm distributing this to the monitored host. Examples here is the agent-based monitoring with the very popular NS client, which is very popular, and we have other good features still in arrive, as we have heard yesterday. Agentless approach via SSH used on Linux and Unix systems. The same agentless approach is working via SNMP for especially network devices or general embedded systems, where I can just study the MIP documentation and address the specific OID to get the counter status of a network device and the traffic which is going over this. Generally, we say it's the historical approach. It was working fine in Nagios. It's still very good in Icinga, so we can still say this is very good. The contrary paradigm is the event-based approach. I accept metrics at all the time, so the remote system is just saying, hey, I have a problem, and I just need to understand the incoming channel, so the protocol which this system is speaking. So I don't need to know always in advance what is coming, but I need just to understand it. So popular example is here the SNMP trap, which is spoken by most network devices. I can just enable it, and it's sending such messages. Email, implementable by most application servers. I can say on the backup software, hey, send me a report each day. Was there a failure on my last backup last night? and I can extract value if there is something going wrong. Syslog, like audit logs, logins, or application errors, I can collect from Windows systems via the event log. Via agent, I can forward it to a collecting system, or also via Linux, it's in the message log or the system CTL, I can forward it also to our central monitoring. New protocols, telemetry, for example, streaming of data is coming on the Cisco devices, which has the idea to send at a more frequent interval status, metric, and performance data. NetFlow in the world of network traffic monitoring, I can derive who is talking with another device. NetFlow is example implemented by Cisco, and I can therefore extract also here from this type of event which kind of communication is appearing in my network. Webhook, another very generic way to subscribe to events from any kind of web-based protocol communication. I can implement by my application I'm developing in the organization, and therefore it's quite a nice way to do it also in today's projects. So we can say this is exactly the moment when an event happens, I will get informed about this. So we have two paradigms, and each of those have advantages, disadvantages. Just to make it, comparing it shortly, the advantage is I can control when a check should be executed in case of polling. I get exactly the information I'm interested in, and I should know the context of the system I'm interacting with. The disadvantage, I could say, it's a static configuration. We have heard it also multiple times this day. Architectures are changing, and our monitoring needs to adapt to this, especially when I have microservices, very dynamic architectures. I need to readapt my monitoring to these situations. I have always continuous cost of resource usage, especially when I'm doing polling day and night, and it's not always possible to retrieve all the data via polling. Advantage of the event processing, it's real time, so I have no delay. I don't always need to know exactly what I will receive, but I just need to understand the channel. And this was the idea. I need to be able to speak many channels and to receive that data. If I have more hosts added to the infrastructure, it's no problem. I just need to speak the channel, and new devices are integrated as soon as they start sending information. Problems I could have, it's in case of a big disaster, there could be a peak of incoming events. I don't want to lose this information, and I need to handle peaks of incoming data. I often have no possibility to filter at source, and especially when the protocol is not reliable, like UDP and SNMP trap mostly is based on this, is a risk to lose such information. But advantages, disadvantages, do we need both of these approaches? In my and our experience doing projects, yes, because we have the advantage to start a project with the polling approach very quickly, easily. We have standard checks. The NETWAYS community was working very good. So they produced a wide range of already ready-to-use checks for health monitoring, for standard checks, and with templates I can create a very good reusable monitoring. And we must also say, with the monitoring automation provided by Icinga, we can also already now adapt to changes in the architecture by interacting with the domain controller, with the VMware controller, and I can read in this information. And as previous talks today also showed us, with Puppet or other automation tools, I can already adapt somehow to these changes. So we see the event-based monitoring as a complement to the polling, and started already with a first initiative in 2013 with a so-called event handler. We were able to speak just the 4 channels: email, SNMP, trap, syslog. We were collecting these events. We were able to create some rules, basically regular expressions. And when an event was coming in, we were comparing it to the regular expression we have in the system. And then we can derive an action. Action was forwarded into the monitoring system. We create a critical, and therefore we can track the historical data, forward the alert to an administrator, and so on. So this was the user interface. It was looking like in our monitoring solution. It was the trend of the incoming data. And it was a very good experience already to gain some let's say, experience, backgrounds, how to work in this environment, but we want to face also the requirements of tomorrow. So the monitoring of tomorrow, in our opinion, is requiring also to handle big amount of data, of events, incoming events, and especially when talking about NetFlow, telemetry, DNS, webhooks, we can maybe handle thousands and even more than thousands events per second. So our problem, we noticed, was scaling is not the point we can face with the current solution, and we need to also adapt to new channels. And therefore we decided, throw it away, rewrite it, and this is the moment to give the word to Francesco.
Thank you.
He will bring us now a nice story how we can, how we were evaluating the introduction and the design of Tornado.
Thank you. So, thanks for the introduction. As Patrick said, we essentially have two ways of monitoring. The first is an active way in which our monitoring solution calls a remote service or host or whatever and try to understand if the service is up, is working, and how it's working. The second way is the one in which we are passive and we receive events from outside. Now, a little bit, I have to perform a couple of steps back in the time just to explain, highlight the relation that we have between how the system complexity evolved during the time and how the way we monitor the systems evolved to adapt to the changes in the systems themselves. So, in the 90s, the systems were very simple, and essentially when something was slow, was not performing well, or used to crash, there was the answer to the problems was to buy new hardware, because new hardware was released nearly every day. And that was a fantastic period, because when the boss was angry, this damn application is slow, you could just reply, well, buy new hardware. It was fantastic. You could drink a mojito, your beer, and enjoy your free time. In the meantime, monitoring was not really a practice, because, and that was something great. So you could write an application, I'm a developer, you could write an application and nobody was able to find the bugs in your application because the systems used to crash much before your application. And that was great. So again, is it working? Was the question. And the answer was, well, if the system is up, more or less, we think it's working. Then, 10 years after, there was a request for more and more performance. We wanted applications to be fast. We wanted to serve more users and to provide feedbacks as fast as possible. CPUs reached their limits. There were CPUs of 3 gigahertz in the 2000, and we still are at 3 gigahertz. So it was not possible to scale vertically, but we discovered that it was possible to scale horizontally. So this means that CPU added more cores, and it was possible to use all these cores to perform computations in parallel. That was a bad moment for the developers, because we could not say to the boss anymore, buy new hardware, because at that point we had to change our software. So our software from single-threaded became multi-threaded, so performing parallel operations on the same hardware. Luckily, we abandoned some strange systems. We had some more stable systems to deploy our software. But still, at the time, the usual way of monitoring was through single pings, simple scripts, most of the time executed manually or maybe in a cron job. So really, the ability to ping or to call a system was enough to say that the system was up. It was still one single machine. You could open your console on that machine, check the process was up, okay, it's working. Suddenly, we entered this hell. So it was not enough to scale horizontally on the same machine. We had to scale horizontally on more machines. So we entered the world of these terms like microservices, distributed systems, and so on. At this point, the complexity of the system exploded. So it's slow, and the answer is even more complex than before. It's not a matter now of parallelized, but it's to distribute. So at this point, we had the systems that communicates with other systems, introducing lots of problems like synchronization, availability, so whatever that comes with distributed systems. And at that point, we started using monitoring tools because it was not possible to go in a machine and simply say, okay, it's working. because now our system is distributed across multiple machines. Maybe you have multiple instances of the same application, or maybe you have different applications that collaborate to produce your result. So at this point, we discovered that these kind of tools were useful. Most of these tools were born with the active monitoring logic. This means that I know that I have 10 instances of this application. I know that I have 100 servers. I open my console. I configure these servers. I send the agent from my monitoring tool, and I expect the agent to run each minute and to report to me if everything is working. At this point, we were happy again, because is it working? Yes, because the board is green, so we have an answer that can provide. The tool is providing us the answer. And then again, this is our modern situation. We don't only have distributed systems, we have distributed systems. We have data centers that contains more than one clouds that contains data centers, and so on. We have geolocalized clouds. This could be in Europe, another one in the US. So the problems of latency, synchronization, the complexity, everything exploded to the nth power. And at this point, to the answer, it's slow. That's the good moment to find a new job, even because so the complexity of the system increased a lot, but your salary probably is the same. So you could find something better, maybe simpler. So what's happened to our monitoring tools? As I said before, we implemented all of our tools essentially based on a polling strategy. That was fine when there was not so many things to monitor, but suddenly now we are in a situation in which we have lots of things to monitor. Not only we have lots of things to monitor, but we have also things that happen at runtime. So, for example, imagine a system in which you add and remove nodes based on the current load of the application. So you cannot configure all your checks up front in your application, because you don't know which servers are running in a specific moment. We saw some examples of Kubernetes, for example. In Kubernetes, you could say, if there are not enough traffic calls, just reduce the number of servers so we can save some money. This does not work with the active logic. So we started integrating into our tools. So we noticed that it is important, it's fundamental for our tools to be able to react dynamically to this kind of events and situations. And here is the point where the passive way of checking the systems became fundamental, because we are not able to actively check anymore. And this is the point also in which not only we started receiving lots and more events, but we also have different type of events. The more and more we go on with the technology, we have IoT devices that are released every day. We have new servers, new operating systems, new applications. All of them send messages and can produce messages which are different. And when you perform active monitoring, you call a system and you say, you must provide me this information. But when you are passive, the system that calls you can pass you whatever it wants. So you could configure your application that works, but at runtime, sometimes add the new nodes to the cluster that tries to communicate with you in a different format. You are not able to handle it. So what should we do? Should we rewrite our applications to handle this kind of load? So all of this, growing and growing and growing in the velocity, variety, and so on, brought us to this beautiful situation. We have our monitoring tools in the middle that are trying to cope with everything is happening outside them. Okay, so again, we lost the ability to use our green board. And is it working? Well, nobody's complaining. We have our support team, nobody's calling them, so maybe it's working. Because at this point, as I said, we are not able to monitor this situation with our classical tools. So we have to guess, again, if something is working or not. So how can we handle with our current tools? We wrote lots of tools. We gained a lot of experience. So we have hundreds of tools and plugins for those tools. What should we do at this point? Should we throw everything away? Should we build everything from scratch to adapt to the new patterns? Or is there a way to just handle these new situations into what we already have? There are some possible solutions to this problem that I'm going to analyze here. So imagine this is our initial configuration. This is something that we configured 10 years ago. we have one monitoring tool, it's one single instance, maybe it's replicated just for availability and crash recovery and these kind of things. And suppose we are able to handle X case messages, let's say 10 case messages. So one could say that, okay, the load is increasing, we have more server, the customer is winning on the market, and so he has to handle a bigger load, so let's just scale our solution. So if we, with one instance, we can handle 10,000 messages, if we can manage 10,000 servers, we just scale it, we deploy 3 instances, maybe 6, whatever, and we handle the load. That could be a simple solution. And in fact, the pro of this solution is that, well, it's simple. You have your solution, you already know it, you worked with it for years, you just have to perform a new deployment, and that's all. It could work out of the box, and it's cheap because, as we said, it does not require additional knowledge or competence or whatever. It has some cons, of course. The first con is that it's not cheap. Well, never. When you distribute something, there is only one category of developers that thinks that distributing something is cheap, is the category of developers that have never done it before. Because when you go from one instance of something to 2 instances, I'm not saying 1,000, to 2 instances of the things, you have to handle a huge set of problems that you cannot imagine before you put your hands in it. It's never cheap. So you don't go to your boss saying, okay, we just deploy another Icinga somewhere. You will lose your job. And the second point is that it does not work out of the box. So it never works out of the box when you go distributed, okay? So for many reasons. First, because we created our softwares, our solutions to be a single point of trust for the entire network. It calls everybody, it lives there. It's not built to communicate, to synchronize with other nodes. We are currently evolving our softwares, but I don't want to say that we are writing workarounds for this, but more or less because we started with something that was not thought since the beginning to work that way. Or, for example, imagine that your suite uses a database. It does not scale horizontally. A monitoring tool, you know that you could also replicate the database that you use to persist your data, but maybe not everybody knows that when you actually replicate your database, the reads become faster, but the writes actually become slower because there is the overhead of synchronization across all the nodes. So a monitoring tool is something that performs lots of writes and few reads when you read the console. So this is not something that helps us to get better performance. And the last point is that all of this leads to the fact that the throughput does not grow linearly. So the first times you can go from 1 node to 10, at a certain point you reach a saturation for the bandwidth, because the overhead of communication and synchronization between the nodes takes more time than analyzing the traffic itself. A single solution that is sometimes used, I saw this one used, and this is a real solution, is to put something like a big data systems in the middle of your events and your monitoring system. So what it means, this is our system, the one we saw before, that receives some events, it works. At a certain point, you have to handle thousands, millions of events. So we can handle only some thousands of them. So instead of sending all the millions of events to our system, we put something in the middle, okay? Someone uses Kafka, someone uses Apache Flume. So the idea is that you pre-process your events, okay? So in a monitoring tool which is built with active checks, most of the time you want to know if something is up. So this means that the majority of the events, the majority of the messages are not important for the system itself. So a system usually is up. So it says, I'm up, we don't care. I'm up, we don't care. I'm up, we don't care. I'm down, this is important for us. So the idea is that we pre-process the messages in a way that we send only the important messages to the monitoring system. So we can reduce the flow that we send to the monitoring tool, and it can keep working. Now, this is a real solution. It's a mature solution. We have tons of possibilities to implement this. The problem of this solution is that this is terribly expensive. So each one of these software, which is highlighted here, which could be Kafka, an Adobe distributed file system, Spark, or whatever you want to put on top of it, Cassandra, it's a beautiful piece of software, but it's very complex. They are resource hungry, so you have to create a cluster only for them. So you could need a cluster only for Kafka and a cluster only for Cassandra, and you need to get the experience to use these tools, because they are not only expensive in terms of resources, but they are also expensive in terms of the knowledge that you need to gain to start using them in a proper way. So you have to hire specialized people, or you have to get the competence. One of the two is expensive. Anyway, as I said, this is a real solution for the problem. This is a beautiful sentence I found in this link. I invite you to read it. Lots of people struggle with the complexity of getting big data systems up and running where they possibly shouldn't be using them at all. So, and in this paper, you can read this unbelievable, first time I read it, I could not believe it. So this guy processed 128 billion edge graph with a cluster of 100 Spark nodes. He was able to process them in 107,000 seconds. And then he wrote a single application, single-threaded, in his machine, and he was able to process exactly the same graph of data in 15 seconds with one single node in a notebook. You can read, and the source code is also in the page, both the one of the edge graph and the one of the cluster and the process. So, as I said before, this is a mature solution. It adds tons of complexity. You can go for it. I'm not here to advise it, but your choice. So as we said, we don't want this one, because mostly it will not work. It will require us to rewrite big portions of this software, which is what we want to avoid more than probably. We don't want to go for this solution. Even if this one is a solution, we would like something maybe like this one, but simpler. So this will allow us to not change this part, which is the one that we already know that it works, that it finds perfect, and so on. But we would like to have this without all of the complexity represented by that box. So we would like something like that, okay? So why don't we have, instead of the monster that was before in the picture, couldn't we have something here, which is simple, which is fast, which is lightweight, which does not require 300 nodes in parallel to print an hello world, that does not need terabytes of RAM, and so on. So, ladies and gentlemen, please welcome Tornado. Okay, so this is the reasoning behind the creation of Tornado. The idea, which one? What's the idea? The idea is that the architecture I presented before is the one that can solve this problem, okay? So we can have an active component that is able to receive the events, process them, and somewhere push them to our monitoring system. But we want it to be simple. We want it to be simple to deploy, simple to configure, not resource hungry. And in fact, it's Tornado, we advertise it as a simple, complex event process, where complex refers to event, not to the environment to process the event. So some feature before I present the architecture. So can you handle millions of events? Yes, our current implementation, the one I'm going to show, can handle millions of events per CPU. Currently, we have the problem that the load that is able to process is much bigger than the events that we are able to pass to it. It's scaled linearly because we removed lots of the complexity of the entire big data stack. We created it to be completely stateless and cloud ready. Stateless means that if you deploy more nodes, they don't need to communicate each other. So if one node can handle 1 million events, 2 nodes handle 2 million events, in fact. This is one architectural decisions. We said that we receive events from lots of sources. Each source tries to communicate with us with a different format. So what should we do? We said that we have to create an application that is able to handle all the possible formats, and every time someone wants a new format, we have to change the source code to handle these new formats too. At the end, we decided to make it simple and to handle one single event format. I'll show you that with one single event format, we can handle whatever kind of code. We want to be able to take decisions based on the event content. So it's not just receiving events. We need to take decisions because, as I said before, some events we don't care at all. We want to be able to read the content and to throw it away. It does not need to burn the CPU, use our resources if we don't need it. In some situations, we want just to forward the event to a system, to an Icinga somewhere. Sometimes we want just to send the event to an Elasticsearch. Someone we want to write it in a database or do all of these things together. It must be simple. As I said before, Tornado accepts only this format of messages. We decided to use JSON because it's the universal language to communicate across systems. And essentially, it's a JSON with 3 fields: the type, you decide the event type, the timestamp when it was created, and a payload. In the payload, you can put whatever you want, which is message specific. Essentially, Tornado speaks only this language here. It has one thing, it's simple because I said before, it receives one single message, it's JSON. It has one single configuration file, and Tornado is one single executable. You download it, you start it in your machine, and you have it working. It's cheap. It's cheap because on commodity hardware, it can handle millions of events. You don't need a cluster of anything. You just have your hardware, you have your deployment of your monitoring tools. You take this executable, you start it in exactly the same machine. It's very unlikely that you will take the resources from your monitoring system because it's very lightweight. It runs with a couple of megabytes of RAM. It's compiled down to native code. It's very optimized, it's super optimized, multi-threaded, using non-blocking I/O. It's intensively tested. We wrote it from scratch with this new language. We are in love with it. It was an experiment. If you don't know it, you should really spend some time with it. The more you want to go low level, the more the performance are important for what you're going to develop, the more this language could be a good choice for you. So, a little introduction about the architecture. This green box here is Tornado, is our executable. And it has some internal pipelines. The idea is this one. We have multiple pieces on different configuration. We call data sources, whatever system can provide information to you. Okay? So a data source could be a database, could be a server, could be a switch that sends SNMP traps, could be whatever. Could be an email. I know that many of us still monitors email and try to get information from emails. So a data source could be an email. So as I said before, Tornado speaks one single language. So it receives an event, which is a JSON that contains 3 fields. So the idea is that for each input, we just have a simple collector. A collector is something that listens for an event in a specific format and transforms that event in the format which is spoken by Tornado. So for example, we can have an SMP trap D collector. This is the message that receives from SMP trap D. We send it to the collector, and the collector simply extracts the data from that and builds what Tornado expects. So a JSON that contains a type, a credit timestamps, and a payload, and that's all. So why this decision? I saw that there are some tools like Tornado that essentially are monolithic blocks in which if you can add the new inputs and new outputs, you can write a new input, and then you rebuild your software, and the input is embedded into the executable. If you do that, you are forced to use, for example, well, as I said, this is written in Rust. You should be able to understand the source code, implement it, use Rust, and so on. But with this decision, maybe you are JavaScript developers. For some strange reasons, you love JavaScript, and you want to send messages from JavaScript. Well, you just build a JSON object, and you send it to Tornado. And you are integrated with the pipeline, with everything. Okay, you use PHP, you love it, you write your PHP that sends a JSON, and you can use it. You love both PHP and JavaScript, you have big problems, guy. Anyway, when the message enters Tornado, this is a concept that was introduced in the talk before this one, so great to know that someone thinks the path is a correct one. When you enter Tornado, the message goes through a pipeline. I will show you in a while. So in a pipeline, we have a set of rules that says where the message has to go, if the message has to be taken into account or just thrown away. If the message is accepted by the system, then we can extract some data, and once we extracted the data, we manipulate it, we transformed it, we can dispatch an action, one or more actions. For example, this message is important for Icinga. because it changes the status of a system. So we call Icinga and say, hey, look that this system now is down. Or we can just execute a script, log, archive, or we can, I don't know, call a logstash, Elasticsearch, write it in a database, do whatever you want. So every message can trigger one or more actions. Oh, sorry, 0 or more actions. The executors are the part of Tornado that performs the real action. So we have some executors that we provide with Tornado itself, and adding new executors, it's pretty simple. It's just implementing one interface, or they can be implemented also as an external system that we call from Tornado itself. This is an example of a pipeline. So imagine that we receive an event which is actually an email. So we receive an email. We have a collector that transforms this email in a Tornado event. So we receive an event which is type email, for example, and then it contains the parsed body of the email as a payload. It enters the root of our pipeline, and then we start checking. Maybe at the beginning, it's quite typical to have a rule that allows every message to flow into the pipeline. And then each time we encounter a node here in the pipeline, we take a decision. Should allow the message to pass or not? In this case, maybe we check that the event type is email, so it does not pass here, here, and here, because this is SNMTP, or syslog, they discard the event. But in this node here, we just check that the email type is filtered, and then the message flows through the pipeline, which can have whatever depth. This is the entire configuration for these two nodes. This is just a node which is active, so all the messages pass through. We use the JSON to describe the rule the condition which is in the filter. This is another filter which is true, which is active. And we're here into the filter, we just check that event.type is equals to email. Okay, so we can apply regexes, we can perform less than equals than, we can perform contains operations and this kind of things. So this is the simplest one, which is equal. This is actually the entire configuration of this pipeline. So everything is here. As I said, we wanted to make it simple. So every node has its own JSON file that describes what happens into that node. And this is not a subset of the configuration. I want it to be clear. This is the entire configuration that you need to create this pipeline. Finally, we said, even into the email filter, we have a set of rules. Every rule can perform some actions. Into the rules, we have additional checks. So, for example, we could check that the email is for the CEO. We perform some actions. It's for someone we don't know, discard it, and so on. And if a rule matches the condition, then it triggers the actions that are bound to that rule. In this case, we have one action. If it was rule 1, it would have triggered 2 actions. This is an example of the rule. The rule is the most complex part because it performs many operations. So I repeat, again, here is the entire configuration of the rule. I just highlighted the important parts. So we want that the type is email, and we check that into the payload, maybe this is an email about the temperature of the server room is too high. I don't know, something like that. Sorry, it's too low, lesser than 50 degrees. So if the event matches all these rules, all these conditions, we can extract some data. We don't have an extractor here. Anyway, we can extract and manipulate some data. It's optional. And here we have a set of actions which are performed if the where clause is matched. In this case, we perform an action which is called Icinga2. We call the process check result API from Icinga, and we set 0 the status of an host whose host name is also extracted from the payload of the message itself. Okay, demo time. Up to you.
Yeah, great. So I just So let's use the last couple of minutes we have here to show you what you have seen from the architecture of Tornado, a simple use case where we receive an event from outside. In this case, we are taking an email, which is a quite simple event. I can receive via text line. In this case, I simulate it very easily on the local system by piping it via MUT on the local system. And create a user. This user is, so in this case, the entry for the channel of the email, and processing the various rules I've created, I will receive an event in the monitoring. So the example here is a simple SIP message. I have an IDOC error with an error code, and there is a good error code. In this example, I take 00 as good, and the other example is the F01. This would be the critical, which is then forwarded into Icinga itself to create a critical situation. So this is the default status. I have here my host, the SIP host, and the status of IDOC in this case is OK. So before showing you all the various steps inside, I just perform the action for sending this message. And as soon we pipe this message into the system, the processing of Tornado performs the rule matching, identifies the error code, and forwards the critical into the system. So how this is working, if I have a few minutes, we have it here. So I can just show you how this was working in the insides of the system. The message itself was forwarded on a local system via mail server into a local collector. As a collector, I have various possibilities. In this case, I implemented the email collector, and this is just listening via configuration file on a specific socket. So I have nothing else than a redirect of the incoming mails to this collecting the socket of the Tornado collector. As soon as this collector went in action, he's forwarding the message into the core of Tornado. Here I have my various rule sets, and as Francesco has indicated before, I can create filters. So my first intention is I differentiate between the various types of events coming in. I have emails, I have webhooks, I have streams of whatever type. So what I first did is I'm creating a filter an expression exactly to filter for the event type email. So the collector at the beginning is flagging this incoming event as a type email. So only events of this type are passing these filters. We can go a step inside, and here I have now the complete rule for interpreting this message. First of all, here I have again the where condition, type end, and I extract from the event.payload.subject the content and compare it to the required sub IDOC. So here I have the first condition. As a filter, I want to say I have a specific error code. F01 is the error code, and I decide if this is matching an action. Here you can understand the typical Icinga API language. I action a process check result, applying the filter of a host name and a service name, and providing the output from the extracted variables on the top. You see in the filter here. So the IDOC error was a variable created with the with condition, and this content and this payload is extracted and written out to the event I'm creating. So we see it exactly here. If I maybe increase it a little bit, you see the error code as the text, and then the full output, which is coming on the bottom. I can do exactly the same for the recovery. I was here, sending the recovery code, and the recovery is arriving. So how this is working inside, I can just open. Let's see the log. If I enable the debug log of the email collector. Sorry. So just send again the critical message, and you see that the incoming message is passed by the collector, extracted the various variables inside this, and forwarded it into the core of the Tornado. If I have a look at the Tornado itself, let's send it again. You see, if I enable the debug level, the various rules he's trying to match, and also the output if there are some rules which are partially matching, not completely right, like it is for the recovery. So in this case, the recovery was not matching and the error was matching. And on the top, you see also the JSON, which was extracted, as Francesco explained before, from the incoming collector. So when doing such integration of other channels, I just need to respect always this language and then able to do it easily. Yeah, principally saying, I would say we can stop here and go back to the slides. Great. So this was exactly now for the documentation. We can publish the slides then on the site, so you can follow again this example on the slides. And with this, we are at the end of the presentation, and we are ready here for questions.
If there are.
Interesting
Thank you.
points.
No.
Thank you. Ah, now it's working. Excellent. You have to shout into it.
Stop.
I see. Thanks. I don't get the hate for Windows 59. I have to admit it's still working in Berlin on this Kammergericht, I think. No. We have, yeah, not working anymore, yeah, I see. I guess we're a little bit out of time, but I guess 2 questions we can still take, and I want to throw. Yeah, excellent.
Ooh,
I don't know if it will go right back there.
Ah, good you are.
Good.
Hello. The talk before was hearing about Sensu, about event pipelines, and I have to admit, it sounded a lot similar to this talk. Where would you see the main differences between Sensu and Tornado?
Up to you. To me. Okay, so yes, we saw the talk, and it was interesting. As I said before, in Tornado we apply some patterns to resolve a problem. And we were quite happy, very happy to see that someone else thinks that these patterns actually works. So the main difference between Tornado and Sensu is the fact that Sensu is a complete product. So if you have to create your architecture from scratch, if you are searching something from scratch, I would say that I think it's a very valid solution. But the objective of Tornado is to provide a simple solution to a complex problem. And the complex problem is something is the one in which you already have maybe a configuration. You have something that runs. At a certain point, you have a problem. Your problem is that you are not able to actively monitor everything. You are not able to handle a specific load. So Tornado can complement your current architecture without requesting you to buy new hardware or to keep additional steps and this kind of things. And it can work as a bridge between passive and active checking, allowing your current architecture to do more with the same that you have right now.
All right, thanks.
You're welcome.
Okay, I guess we have time for one last question. Nobody? Okay. Oh, right in the front. Do you dare to throw? Up there.
There.
Just try it. Excellent.
Hi. Is it ready for production, and do you have a roadmap for the product?
Well, is it ready for production? Yes, it is already in production in our installations of NETWAYS, in the latest versions at least. And we have a roadmap. Yes, it will be, everything is open source. Of course, here you can see the link. The roadmap will be published soon. We currently built the core of the software. There are many new features that we want to integrate with it. Okay, there's no time.
Yeah, but as you told, it's open source. There are also some nice examples, so you can read a reference guide. So there should be at least some instructions how to can you build your own test cases, and maybe if you use another monitoring system, I don't know if you use Nagios or Icinga or whatever, so you can also find probably some instructions how you can also do your first examples with this. Yeah, but it's working. And yeah, just to add, I created during my consulting activity also some examples. Also, last one was of Tornado, creating a simple web request. I published it on the GitHub of my personal account, so you could have a look maybe there to find some ideas of a first instruction to create a webhook subscription to this case. Yeah.
Excellent. Thank you again.
Thank you.
Thank you.